All right, 2.2, Introduction to Polynomial Functions. So a polynomial function is going to be a function, and it has a few special properties. Now, polynomial functions are really, really nice for a number of reasons. In calculus, you're going to learn to love them. Here are the properties that polynomial functions have that define them as polynomials. So the first property, there's no x in the denominator. The second property, there's no x inside of a radical. And then the third property, there's only positive whole number exponents on x. So what you're going to see a lot in calculus and a little bit in this class here is that graphically, polynomials are really nice. They're smooth curves. They don't have breaks or corners. And maybe I'll write that down just now. All right, so they're smooth everywhere, no breaks or corners. They're nice graphically, which is the reason we're talking about them now. So let's do an example where we determine whether or not something is or is not a polynomial. So looking at this first one, we have 9x minus 2x cubed. There's no x in the denominator, there's no x under a radical, and the powers on x are all positive whole numbers. So technically there's a 1 here, but 1 and 3 are both positive whole numbers. So this guy right here is a polynomial. For this next one, now you have to be careful because we do see that there's a denominator here. However, the rule said there can't be an x in the denominator, and there's no x in the denominator here, so it doesn't violate that first rule. The second rule, there's no radicals, we don't have to worry about that, and the exponents on x are both positive whole numbers. It's okay that this guy doesn't have an exponent, it's just if there is an x with an exponent, it needs to be a positive whole number. So this guy right here, we can call him a polynomial. Looking at this next one, we do see an x under a radical, and polynomials don't have x's under radicals, so this guy is not a polynomial. This one's a bit tricky. So g of x equals 8. You might say to me, well, there's no x in it, so how could it be a polynomial? It's a polynomial. It's a very boring polynomial. What's most important is that you don't violate any of these rules. As long as you haven't violated a rule, you're a polynomial. So this doesn't violate any of the rules, therefore it is a polynomial. Constants are polynomials. So a constant function is going to be like f of x equals a number, just a number, no variables. Constant functions are all polynomials. And then finally, we have this guy down here. Now, we're looking good, 9x cubed, 5x squared. However, with the last term, there is an x in the denominator. And because there's an x in the denominator in one place, it ruins the ability for us to call it a polynomial. So if it fails once, it fails for the whole function. This entire function cannot be called a polynomial. Let's go ahead and do a little bit of a review from the stuff we covered on the first exam. This is going to come in handy later. That's the reason we're reviewing this. We're about to expand upon this idea, but let's do something that we did a little earlier and find the x and y intercepts of the graph of a function. So if you remember, so this is our function. For the x-intercepts, that's where you let y be 0. Now, if there's no y, which we can see there's no y here, f of x is really just the same thing as y, so you would just make the f of x part 0. So 0 equals x cubed minus x squared minus 9x plus 9. This is going to be a factoring by grouping problem. If you don't remember this, there's some problems from the very, very beginning of the course in that factoring topic that you can go back and look at. So for the first group, I'm going to factor out an x squared, and I'm left with an x minus 1. For the next group, I'm factoring out a negative 9, and I'm left with x minus 1. Now I have an x minus 1 in both of these that I can pull out. So I'm pulling out the x minus 1 from both of them. And what's left is the x squared and the minus 9. X squared minus 9 is a difference of squares, and it factors into x plus 3 times x minus 3. Now remember, you would set each of these equal to 0, and that's how you'd find the x-intercepts. So, oops, I just zoomed it in. I was trying to drag it down a little bit. So our x-intercepts are at 1, 0, negative 3, 0, and 3, 0. Those are our x-intercepts. Now, Alex asks for your x-intercepts as just the number part. So Alex just wants you to use this part here, but really the x-intercepts are the entire coordinate point. For the y-intercept, this is where you plug in x equals 0. And for this, I'm going to go all the way back to my unfactored form and plug in 0 there. And you'll see why. So 0 cubed minus 0 squared minus 9 times 0 plus 9. Everything disappears except for the 9. So here we have a y-intercept at the point 0, 9. Okay. So those are the x and y intercepts of a graph. We're going to go ahead and expand on that idea now. So let me go ahead and introduce to you a new but similar idea, the idea of a 0. So the x values of the x-intercepts of a polynomial are known as the zeros of a polynomial. So I want to make note of the difference between an x-intercept and a 0 because they are different, although Alex treats them as if the words are interchangeable, and sometimes I treat them as if the words are interchangeable. But I think it's worth pointing out the difference between the two. So an let me get my pen. An x-intercept is a coordinate point. So if I draw a picture right here with some graph, the place where it crosses the x-axis right there, let's say it crosses at 1, we would say that the x-intercept is at 1, 0. The 0 of a polynomial is the x value of the x-intercept. It's also the value that makes the polynomial 0 when you plug it in. Well, maybe not, it's the number. It makes the polynomial 0 when you plug it in, is what I should say. Equals 0 when you plug it in. So for instance, if we had the function y equals x minus 1, which is conveniently this picture that I have drawn over here. So if we have y equals x minus 1, then when you plug in, so I'm going to claim x equals 1 is a 0. It's the only 0 for this one. When you plug it in, y equals 1 minus 1, you get 0. So that's why we call it a 0, because when you plug it into the polynomial itself, you get 0. So really, zeros are used in a more algebraic sense, even though they have relations to a graph, whereas x-intercepts purely relate to the graph. They are the place where the graph crosses the x-axis. Now, once again, Alex is going to use these kind of interchangeably, but they are different. So for my second note, I want to go back to this previous example. We have a bunch of x-intercepts, and we can say that because we know the x-intercepts, that we know the zeros of the polynomial, right? So the zeros of f of x are just the x-coordinates of the x-intercepts. So we have 1, -3, and 3. Now look at where they came from. So 1 came from the factor x minus 1. -3 came from the factor x plus 3. And 3 itself came from the factor x minus 3. So whatever the 0 is, when the polynomial is factored, the factor that it comes from is going to have x minus the 0. And that's what my note number 2 is going to be. So, note 2. If c is a 0 of a polynomial, then x minus c is a factor of the polynomial. So if I were, for instance, to have a polynomial that was x minus 1 times x plus 2, the zeros from these guys have the opposite sign from their factor. So this was a plus, but it gave us a -0. This is a minus, but we got a positive 0. So x minus the 0 is an important fact. Now, I have kind of mismatched my way through this lecture, and I've taken slides and redone them and stuff, so you're about to see a flash of a slide that looks slightly different than this one. It's because I'm a mess and I can't lecture straight. So ignore that the next slide you see is briefly not what you're seeing now. So let's go ahead and do an example that uses this fact. So form a degree 3 polynomial whose zeros are -2, 0, and 2. And I want to talk about this degree 3 thing. The degree of a polynomial is just the highest exponent on x. So when we're forming a degree 3 polynomial, it means that the highest exponent on x should be a 3. Now, to kind of elaborate on this fact and not solve the problem right away, if you have x plus 7 times x minus 4, this is a degree 2 polynomial because when you multiply it all the way out, you would get an x squared term as your highest term. If I have x plus 7 squared times x minus 4, this would be a degree 3 polynomial, even though it's not FOILed out at all, because if you FOILed this guy, you'd get an x squared, and then if you multiplied the x minus 4 in, you'd get an x cubed in there. So really, as long as something's in factored form, to know what degree it is, you could just add up the degrees of each of the factors. So if I made something like x to the 5th It's a really bad 5. X to the 5th, x plus 7 cubed times x minus 8. The degree of this guy would be 5 plus 3 plus 1, because there's like a secret 1 here. So the degree of this guy would be 9. Right? So that's just kind of an aside, not relevant to the problem, kind of relevant to the problem, not 100% relevant to the problem. So forming a degree 3 polynomial whose zeros are x minus, or minus 2, 0, and 2, what we need to remember is that x minus the 0 is a factor of the polynomial. And these guys right here are my zeros. So if I'm making this polynomial, I'm going to call him f of x. It should be x minus, my first 0 is negative 2. So x minus negative 2. My next one, x minus 0. My next factor, x minus 2. Now, this isn't super beautiful the way it's written, so let's go ahead and make it a little bit more beautiful. When you're subtracting a negative, that's just a plus. X minus 0 is just x. And then we have x minus 2. But you notice how in this guy, if there was just an x that we put him out front, we're going to go ahead and do that. So we'll take the x and we'll just put him straight out front. And then we have x plus 2 times x minus 2. And I want you to take note of the shortcut we can make right now. If you have a negative 0, that means that the factor will be a plus sign. So it's really just the opposite of what you see. So you don't really need to write the minus and negative part out. You just need to know that if you're subtracting a negative, it would turn into a plus sign anyway. Now, if I wanted to verify that this was a degree 3, maybe I didn't trust any of the stuff that I set up here, we could do that. I'm going to start by multiplying together x plus 2, x minus 2, because that's a difference of squares. It multiplies to x squared minus 4. And then we get x cubed minus 4x. So the highest degree is a 3. So that was just checking to verify that it was a degree 3 polynomial. Let's go ahead and do another one. So here we're told to form a degree 3 polynomial whose zeros are negative 3 and 1. Now, I'm not sure if Alex does this to you, but I just kind of wanted to talk about this situation. So same idea as before, we do want to do the x minus the 0 when we set up our polynomial. And we have two zeros. We have negative 3, so that would be x plus 3, right? Because it's the opposite of what we see. So if it's a negative, it's a positive in the factoring. And x minus 1. However, this would be a degree 2 polynomial, right? If you FOILed this out, you'd get x squared minus 2x minus 3, which is degree 2. Oh no. Now, we were specifically told what the zeros of the polynomial should be, but we didn't say anything about how many times they could be repeated. So we can't just add in a new 0 here because that wouldn't follow the criteria of these being the zeros. But what we could do, and we have two options here, you can square one of the zeros. So I could square this 0 right here, and this would make a degree 3 polynomial. Or, if you wanted to, you could square the other factor. So x plus 3 times x minus 1, and this guy is quantity squared. Either of these are valid answers, so they're both going to be degree 3. I could FOIL them out, but I'm not going to do that. But if you would like to verify, totally fine. But either of these will be degree 3 polynomials who has negative 3 and 1 as zeros. So let's go back to, oops, thought I had my pointer. let's go back to talking about this. Notice how sometimes I put like a number up here on each of the factors, and we said we could add them together to find the degree. There is a specific name for the power on each of the factors in a polynomial, and we call it the multiplicity. So each zero has a multiplicity, and the multiplicity is going to be just the exponent on that factor. So let's go write that down. The multiplicity there we go, of a zero is the number of times that that zero was repeated, is kind of the technical meaning. But the more useful meaning to us is going to be it's the power on each factored piece. Let's go ahead and do an example. So we're going to find the zeros and the multiplicities of each of those zeros from a factored polynomial. Also, the word multiplicities is really long to write out. Just thought I'd throw that out there. All right, so we have 9 times x minus 7 squared, x plus 6 squared, x minus 4 cubed. All you're going to do to find the zeros is, it's the same as finding your x-intercepts. You take each factor and you set it equal to 0. And then the multiplicity is just the exponent. Now, this very first guy, the 9, if you try to set it equal to 0, you just get 9 equals 0, which that's not a true statement. So 9 doesn't have anything to do, if it's just a constant out front and there's no x, it has nothing to do with the zeros and the multiplicities. So there's nothing to deal with the 9. Here, we'd have x minus 7 equals 0. So x equals 7 is the 0. And then the multiplicity is 2. Here, x plus 6 equals 0. So x is equal to negative 6. And the multiplicity on this guy is 2, because that's his exponent. X minus 4 equals 0, x is equal to 4, and his multiplicity will be 3 because that's the exponent on him. And those are our answers there. Ooh, let me use blue. Let's go ahead and do one more example where we're finding the zeros and the multiplicities. So before, I only had a 9 out front, and that's why I ended up saying, don't worry about it, he doesn't really do anything for us. However, if there's an x out front, you're setting that whole thing to 0. So you could include the 2 if you wanted, although you don't need to. It comes out the same either way. 2x to the 5th equals 0. That's just going to give you x has to be 0. And the multiplicity is that exponent on x. So this will be multiplicity of 5. Here we'd have x minus 1 equals 0, so x is equal to 1. Now he doesn't have an exponent written here, but if there's nothing written, we can just put a 1 in. So his multiplicity would be a 1. And then finally, for x plus 2, we would set him equal to 0. We'd get x equal to negative 2. And his multiplicity is also 1 because there's no number written there. And that's that. So I kind of want to bring this back to nonlinear inequalities. Now, if you remember from, first of all, let me just write what I'm talking about. Nonlinear inequalities. If you remember, one of the things I talked about in class, let's just make ourselves a random inequality here. We talked about doing a sign chart for these. So you get x equal to negative 1, x equal to 2, x equal to negative 4. And we talked about what was really happening here is that we would have some kind of graph like this that we would never see. And greater than 0 meant that we were above the x-axis. We were asking for which intervals of x is the graph above the x-axis. So here, those x values, these x values, this is a random graph, not related to what I've drawn over here. But that's what it's asking, is when it's above the x-axis. I want to point out what happened when we had, where's my drawing? What happens when we had a even multiplicity, but we didn't call it a multiplicity there, an even power in a factored nonlinear inequality. So if you remember, put negative 4, negative 1, and 2. I'm just going to do a test value for the first one. So plugging in negative 5, I get negative. And then this guy is positive because he's squared. So negative 5 minus 2 is negative, but you square it and it's positive. And then negative 5 plus 4 is negative. And altogether, this guy right here is a positive. And then I said, so the only thing that can happen at each 0 is that whatever this 0 is, that factor can change sign. And it will change sign as long as it has an odd multiplicity. So when I go from this column to this column here, negative 4 came from this factor, so the only factor that should change is that this negative should go to a positive. And indeed, if you look, when I plug in, if I used a value here, if I used x equals negative 2, negative 2 plus 1 is negative, so it remains negative, and the middle term is positive. So this guy right here is negative. Once again, when we move to the next column, when we pass by negative 1, we're looking at this factor here changing from negative to positive, but nothing else will change. And that's all fun, but what happens when we get to 2? Because he's squared, he doesn't change from a positive to a negative, he just stays positive the entire time. He doesn't change at all when you swap over. So when you move to the next column, even though with all the other ones, right, when you went over negative 4's factor turned an opposite sign. When you moved over negative 1, his factor turned the opposite sign. But it doesn't happen if you're raised to an even power. So if the positives and negatives are relating to what's happening on my graph, where the graph is, then just kind of some really bad sketching about to happen here. So it says that before negative 4, that the graph is positive, so it goes, so it's here, so it's positive, it hits at negative 4, and then it goes negative all the way up until negative 1. So all I'm going off of right now is positive means above the x-axis, negative means below the x-axis, and these numbers are x values. Right, and then it's positive up until 2, and then it has to stay positive there. If it stays positive, it has to bounce off the x-axis. So I want you to keep that in mind, that the power on each factor kind of related whether or not it could cross the x-axis. And now we're talking about the power on each factor being called a multiplicity. So let's expand. So if you have an even multiplicity, your graph is going to, get rid of that, your graph is going to bounce there. It's going to bounce off the graph, off the x-axis. Oops. Graph bounces off x-axis. At that 0. So, quick little sketch. If your 0 is right here, it would bounce right off. If you have an odd multiplicity, your graph is just going to pass through the x-axis at that 0. So here's my 0, or my x-intercept, and it's just going to pass through the x-axis instead of bouncing. Now let's talk about a concept called end behavior. So the end behavior of a polynomial is essentially what it does when it leaves to the left or right of a page. So if I draw a really crappy picture right here, and let's say that my graph looks like this, the end behavior is just the fact that when it goes off to the left here, it goes up, and when it goes off to the right, it goes down. So the end behavior is just what's happening at the very edge of your graph as it leaves your page. And this is going to depend on two different things. Maybe I should just leave that picture there. One, it's going to depend on the degree, whether it's even or odd. So what influences end behavior? So degree, so even versus odd. And then the coefficient of the leading term, whether it's positive or negative. So the coefficient of the leading term, I'm going to, ooh, that's not a very pretty, there we go. I'm going to call this LC, so like leading coefficient. I'm going to call it LC for short as we talk about end behavior. Now, disclaimer, talking about end behavior actually isn't 100% necessary because we have the tool of nonlinear inequalities. So we actually don't need to talk about end behavior, but I would be a bad teacher if I didn't. So let's talk about end behavior. All right. So if the degree of your polynomial is even, then the end behavior of your polynomial is going to go up in both directions if the leading coefficient is positive. If the leading coefficient is negative, it's going to go down in both directions. If your degree of your polynomial, if your degree is odd, they're going to go in opposite directions. If your leading coefficient is positive, it'll go down as you leave to the right or the left, and it goes up as you leave to the right. And if your leading coefficient is negative, it will be the opposite. So up here, down here. So I'm going to use this to do some of the graphing, but I'm also going to use the nonlinear inequalities to do some of the graphing, just so you can kind of get a hang of how to use either of them. Let's look at sketching this polynomial, x cubed minus x squared minus 6x. The first thing we need to do is factor this guy so we can find his zeros. So I can factor an x out of everything, and then I have x squared minus x minus 6, and that'll factor into x minus 3 times x plus 2. So I have x equal to, not 1, but 0, and his multiplicity is 1. I have x equals 3, and his multiplicity is also 1, because there's no exponent on the factor. I have negative 2, and his multiplicity is 1. Each of these multiplicities are odd, which means that the graph is going to pass through at each of these zeros. Hold on, my dog is barking. All right, so if I am drawing a sketch right now, I know that there's a 0 at 0, 3, and negative 2, and the zeros are the x-intercepts, right? They're basically the x-intercepts. So we know we're hitting here, we're hitting here, and we're hitting here. In order to determine what the graph looks like, we have two options. We can either use the end behavior from the previous page, or we can do a nonlinear inequality. If we're using the end behavior, we have a degree 3, so that's odd, and the leading coefficient is technically a 1, because there's technically a 1 right here, so that's positive. So odd degree, leading coefficient positive, we're looking at end behavior that looks like this. And now my other dog's at the door. Hold on. All right. So I know that when it leaves the page, based on what my end behavior said, it should be going this way. Ooh. And this way. I also know that at each of the zeros, it should just pass through. So pass through the x-axis. That didn't hit very well. Pass through the x-axis there, pass through here, pass through there, and bam, we got ourselves a beautiful graph. Now, let's go ahead and assume we didn't know anything about end behavior. And erase. We could also do a nonlinear inequality here using these zeros. So we have negative 2, 0, 3. I'll just go ahead and do all the work of a nonlinear inequality. So I have my test points, and I'm plugging them into this guy here. So plugging in negative 3 to x, you have a negative. Negative 3 minus 3 is negative. Negative 3 plus 2 is negative. This whole thing is negative. Negative 1 is negative. Negative 1 minus 3 is negative. Negative 1 plus 2 is positive. So this is positive. 2 is positive. 2 minus 3 is negative. 2 plus 2 is positive. This whole thing is negative. 4 is positive. 4 minus 3 is positive. 4 plus 2 is positive. This whole thing is positive. So what this is telling me is that prior to negative 2 is right here, prior to negative 2, you should be below the x-axis. So that to me means it had to have come from this way. Positive means above the x-axis. So it's above the x-axis between -2 and 0. And you could argue maybe it's supposed to go up higher. It doesn't matter. Sketching it, just do your best. All right, between 0 and 3, we are below the x-axis. And then after 3, we are above the x-axis. So you'd get yourself the same type of graph. We'll go ahead and do one more sketching polynomial problem, and that'll be it for this lecture. I know it's already long enough, but we're almost there. So if we're asked to sketch this polynomial, we're first going to need to find the zeros. So here, x equals -1 is a 0, and his multiplicity is 2. Remember, that's the exponent on the factor, so 2. For x plus 3, my 0 is -3, and his multiplicity is also 2. Remember that this guy up front doesn't have a 0 attached to him unless there's an x here. There would have to be an x, like there was out here, to use him. Otherwise, if it's just a number, we're not going to use him. Both of these multiplicities are even, which means it's going to bounce at those zeros. So if I go ahead and make myself a graph here, there's -1, I have an x-intercept there, -2, -3, and I have another x-intercept here. Two options. Either we're using degree and leading coefficient to determine end behavior, or we do an inequality. If you're doing degree and leading coefficient to do end behavior, the degree here, you add up the multiplicities. So the two multiplicities, 2 plus 2, so we have a degree 4, so it's even. The leading coefficient, you're really just taking whatever the x term is and applying whatever exponents on it, and then whatever is out front. So this would be a -3, an x squared, which would give you -3x to the 4th. So it would be a negative leading coefficient. So even degree, negative leading coefficient. We're looking at this picture here, so it should go down in both directions. But I'm going to go ahead and do a chart for funsies. So you have -3 and -1. I'll choose -4, -2, and 0. Now remember, because of this -3, there's going to be a negative in front of all of them because there's a negative in front of the polynomial. Now, the kind of nice thing is, because both of these are squared, it doesn't matter what you plug in, right? If I plug in a negative, once it squares, it'll be positive anyway. So both terms are like that, so they're never going to change sign, which means it should be below the x-axis at all times, which agrees with this guy right here. So you come down, bump, bump, something like that. We could have found the y-intercept here to make it a little bit more exciting, but we're looking at a rough sketch here. So that's that in terms of sketching polynomials. You're really just looking at the multiplicities to determine whether it passes through or it bounces, and then either using your chart to figure out if it's above or below the x-axis, or using end behavior to fill in the rest of your graph. So that's that for this section. If you have questions, feel free to email me. Otherwise, have a fantastic day, and I will see you in the next video.